Now we're going to do a really big vector addition problem. You're going to have two problems like this in your pre-lab. The method that I'm going to work through here is exactly the same as the method that you're going to use to solve both of those questions where you're being asked to solve for a third force. Determine a third force such that the sum of the forces F1 plus F2 plus F3 equals 0. And in this example problem, we're going to figure out what is the magnitude of that third force, its size. And we're also going to figure out what angle this vector makes, vector F3, with respect to the positive x-axis. So in the two Canvas problems that you have that are similar to this, one of them is going to ask you just what is the magnitude of F3, and then the other one is going to ask you what angle does F3 make with respect to the positive x-axis. And so you'll have to do two different problems with two different numbers. One of them will ask you for the magnitude of F3, one of them will ask you for the angle of F3. And so what we're going to do is work through one problem, and I'm going to show you how to solve for both of those to keep me from having to go through two separate individual problems, because the method is the same. You just only have to solve for one instead of the other in the two problems that you see that are similar to this below. Okay, so let's start with what we are given. We are told that we want to consider two forces, force F1 and F2. Their magnitudes are, so my magnitudes, their size for that vector, vector F1 has a magnitude of 26.06 newtons. This big N is a new unit that we're encountering called a newton, okay? And then F2 is equal to 18.11 newtons, the magnitude of F2. So I put the bars around the vector. That means that that's a magnitude, that's the size. So when you see this N, that just means newton. And 1 newton is equal to 1 kilogram times meter over seconds squared. And then we give it the special name of Newton for the special unit of force, named for Sir Isaac Newton, who's so very important for us in physics. And we're also going to talk eventually about Newton's 3 laws in our lecture class. Okay, so that's the unit of Newton. Okay, and our first angle is at an angle of 46.07 degrees with respect to the positive x-axis. Our angle F2 is 112.09 degrees with respect to the positive x-axis. So with just that information, we need to figure out what is the magnitude of F3 and the angle F3 makes with respect to the positive x-axis, such that F1 plus F2 plus the vector that we're solving for, F3, equals 0. So that means that these forces are going to be in equilibrium. The sum of all of them equals 0. So where do we start? Okay, the first thing I always do when I'm given a problem like this, the only thing I know is the magnitude and the direction of the force. I want to break up that force into its x and y components. And then I want to write out this vector in its vector notation, unit vector notation. So what I'm going to do is start by drawing out what does vector F1 look like. Let's make a sketch. So here I've got the origin of some coordinate system. And I know that this vector is 46.07 degrees with respect to the positive x-axis. So that's this way, okay? And then up is my positive y-axis, okay? So that means that my angle is going to go off in sort of this direction right here, or my vector, I mean, is going to go off in sort of this direction right here, with this angle right here, which I'm going to call theta 1, equals 46.07 degrees, okay? So this solid line here that I drew with the arrow tip, that is my vector. And these dotted lines here, these are the x and the y components of this vector. So we have to figure out what are these x and y components of this vector. This is vector F1 with a magnitude of 26.06 newtons. Okay, so this component along the x-axis of my vector, we are going to call that F sub 1 x. And we're going to call this component of my vector f sub 1 y. Okay? So if I look at this angle right here, let's start. So I see that fx here, the x component of this vector, is adjacent to this angle. So that tells us that I can use that cosine of angle theta 1 is equal to my adjacent side, which is the x component of my first vector, over the hypotenuse of this little right angle triangle we have, which the hypotenuse of this triangle is the magnitude, the size of this vector. Okay? So this tells us then that the x component of my first vector is equal to the magnitude of my first vector cosine of that angle. Okay? And so then if I go ahead and stick in the numbers here, then we've got the magnitude of this vector is 26.06 newtons. Cosine of my angle was 46.07 degrees. So this component here, f1x, is equal to 18.08. Okay? So this is equal to 18.08. All right. So for the y component of f1, if I know that I had to use cosine of this angle theta to get the x component, then I have to use sine of this angle to get the y component, because f1y is opposite of my angle here. Okay? So then I can say that f1y is equal to the magnitude of f1 sine theta 1. So that's going to be 26.06 newtons. Oh, these also have units of newtons, these components, okay? Times sine of my angle of 46.07 degrees. And so that gives me a component of 18.77 newtons. Okay, so this is equal to 18.77 newtons. So here's the x component of my first vector. Here's the y component of my second vector. Let's write that out in vector notation. And I'm going to do that in this little space right here. So if we write f1 out in vector notation, then let's see how this blue works. f1, that's okay, is equal to 18.08 newtons in the, we'll use x hat, we'll use I hat and j hat in the I hat direction, plus 18.77 newtons in the j hat direction. Okay, so that's what vector f1 looks like in vector notation. So I know that this component is the x component of that vector. This component is the y component of that vector. Okay? Now, let's do the same thing for vector f2. So, I'm going to come over here. Vector f2, I'm going to draw it like this. Okay? Here's the positive y-axis. Here's the positive x-axis in this direction. Now, vector f2 has a magnitude of 18.11 newtons at 112.09 degrees from the positive x-axis. So remember from geometry that if you would start here on the positive x-axis and go all the way over to the negative x-axis, that would be 180 degrees. Straight up along the y-hat axis, from the positive x to the positive y-axis, that would be 90 degrees. So this angle, 112.09, is going to be pointing off in this direction over here, because we had to go to 90 and then just a little bit further. So this whole angle right here is the 112.09 degrees. Okay? So this angle right here, which I'm going to call angle alpha, alpha is going to equal 180 degrees minus 112.09. So alpha here is equal to 67.91 degrees. Okay, this is the angle that I'm going to use to help me figure out the x and y components of my vector F2. So let's label vector F2 has a magnitude of 18.11 newtons. Okay, so that's its size. That's its a measurement of its size. Okay, so now just like we did for our vector F1, we can find the x and y components of this vector. And I'm going to use this angle alpha here to do that. So this side here would be F2x. This side here is F2y. Okay. So just like over here, let's start with cosine theta, or cosine alpha, equals, so cosine is equal to the adjacent over the hypotenuse. So cosine of this angle right here is going to tell me that is equal to the adjacent side, which is the x component of this vector, over the hypotenuse, which is the magnitude of vector F2. So F2x equals the magnitude of vector F2 cosine alpha. So this is going to be 18.11 newtons cosine of this angle here, 67.91 degrees. Okay, and that is equal to 6.81 newtons. Now, just like the other pre-lab that we worked on for the vector lab, you have to think about the direction of your vectors. So vector F1 went over in the positive direction and the x up in the positive direction in the y, so those components are positive. This vector F2 went to the left, negative x component, so I have to remember I've got to put a negative component here on this vector. So the component of vector F2 in the x direction actually is negative because it's moving to the left. Now, F2y, since the x component was cosine, I know that the y component is opposite from this angle, so it will be the magnitude of F2, not cosine, sine alpha, okay? And so that's 100, or I keep on saying that, 18.11 newtons sine of our 67.91 degrees. And that is equal to 16.78 newtons, okay? And so this component, the y component, is positive, so we don't have to worry about putting any other sign out in front. We could just remind ourselves that these are positive, okay? This one for the x component of F2 is negative because we're going in this direction, okay? Just because our angle was bigger here than 90, so we're going up in this direction. Now we want to write F2 in its unit vector notation. So we're going to come over here and I'm going to say that F2 is equal to, its x component is minus 6.81 newtons I hat plus 16.78 newtons j hat. Okay, so this is what our vector F2 looks like in unit vector notation. It has a negative component for the x component and a positive component for the y component, okay? So then what we're going to do, now that we have the x and y components of these two vectors, we can use them in the same way to the previous problem that we worked on in order to figure out what the x and y components of F3 are, and then we can figure out its magnitude and the angle that it is with respect to the positive x-axis. So I erased this whole side of the board. We can have more room now. We already found vector F1 and F2 in its vector notation form, so we've got the x and y components for both of them. Now we need to figure out what is F3. And to do that, we're going to use the same method as the previous problem that we worked on, where we know that if all these vectors have to add up to equal 0, that the x components have to add up to equal 0, and the y components have to add up to equal 0. So the sum of all my forces in the x direction must equal 0. So then we'll have f1x plus f2x plus f3x equals 0. Okay, I solve this equation for f3x, so I'll subtract both of these terms to the other side of the equal sign. f3x is equal to minus f1x minus f2x. Now, I can just plug in those numbers. f3x is equal to minus, or negative, and then the x component of f1, so that was 18.08 newtons, minus the x component of f2, so that would be minus negative 6.81 newtons, okay? And then we've got a minus, and then minus a negative number, so then that becomes positive. And this is minus 11.27 newtons is f3x, okay? Now, for the y component, we do the same thing. Sum of the forces in the y direction equals 0, so f1y plus f2y plus f3y equals 0. So we solve for f3y. f3y is equal to minus f1y minus f2y. This is equal to minus our y component of f1, 18.77 newtons, minus the y component of f2, 16.78 newtons. And so this is equal to negative 35.55 newtons. Okay, so we've got the x and y components of this vector. What does this vector look like then? We know the x components, we know the y components, so let's see, we'll draw a little sketch. So if I start, let's start here. Okay, this is the positive x-axis, this is the positive y-axis, here's my negative x-axis, okay? And so for this vector f3, our x component is minus 11.27 newtons, so it's we have to go to the left 11.27 newtons. So this component here, f3x equals minus 11.27 newtons, okay? And then the y component is minus 35.55 newtons. So this is f3y equals minus 35.55 newtons, okay? And so then the vector that I can draw in for vector f3x is the vector that will start right here and go all the way down this way. We had to go over in the x and down in the y, okay? So then we have this vector here where we essentially have made, again, a little right angle triangle. So my vector here, that's the hypotenuse of this right angle triangle, and then we have the x component of that triangle and the y component here, okay? So to find the magnitude or the size of f3, we can use the Pythagorean theorem. So the size or magnitude of f3 is going to equal the square root of f3x squared plus f3y squared, okay? So that will equal to the square root of minus 11.27 newtons squared plus minus 35.55 newtons squared. And then that answer turns out to be 37.3 newtons. So the magnitude of this vector, its size, is 37.3 newtons. But that's only one part of a vector. The magnitude is only one part of the vector. We have to get the angle that this vector is with respect to the positive x-axis. So if this is the positive x-axis, the angle that this vector makes with the positive x-axis is this angle that goes all the way to here, okay? This angle that goes all the way from the positive x goes all the way through 180 degrees and just down here, okay? That's the angle that we would want to report in the question space for Canvas. What is the angle that this vector would make with respect to the positive x-axis? So what we can do is we can find this angle right here, okay? This angle right here that I just drew with the sort of 3 arches here, we find this angle right here, add it to 180 degrees, that gives me the angle that I am with respect to the positive x-axis. So to get this angle right here, which I'm going to call this angle beta, Greek letter beta, okay? So we can use tangent of beta. Tangent of beta is equal to opposite, which is the y component of my third vector, over adjacent, which is the x component of my third vector. So to get beta, we have to take the inverse tangent of both sides. So beta is equal to the inverse tangent of f3y over f3x. So that is equal to 72.41 degrees. Okay, so that's what this angle is right here. But we need to report the angle that we are with respect to the positive x-axis. So that angle is going to be 180 degrees plus 72.41 degrees, and that will be 252.4 degrees. Okay, so that would be the angle that you would report with respect to the positive x-axis. So now we just did our problem. We found what force, F3, do we need such that the sum of F1 plus F2 plus F3 equals 0. We found that vector by breaking up our other 2 vectors into their unit vector notation. Then we solved for vector 3 and found its x and y components. We used that to get the magnitude of our vector, and then I drew it out here, and we can help us understand what our angle should be with respect to the positive x-axis. So we found this smaller angle down here and added it to 180 degrees so that we could get that here.